I am Professor Wim Bogaerts from Ghent University and IMEC, and I'll be chairing this second session of this China-Europe Symposium of EPICS-FAB. And we have 4 exciting talks in this session. Well, I think by now you all are very familiar with the idea that in silicon photonics, it's not just about photonics, it's a combination of photonics and electronics. And this is what our first speaker, Professor Nan Qi from the Institute of Semiconductors at the Chinese Academy of Sciences will talk about to us. He will be speaking about silicon electronic photonic co-designed ICs for co-packaged optics in high-speed data center interconnect. Professor Nan Qi, please, the floor is yours.
Thank you, Professor. Can you see the slides?
Yes, we can see your slides.
Okay, thank you. Good morning and good afternoon, everybody. Welcome to this talk. My name is Nan Qi, and my topic will be the co-designed integrated electronic circuits for the silicon photonics that used in the CPU in the data center. So this some of the works in this presentation is in the collaboration with WRI, National Optoelectronics Innovation Center, and Shanghai Jiao Tong University. So this is the outline of my talk. We'll go through the background and motivation, and then the detailed challenges and solutions, especially the co-design of both electronics and photonics. And finally, we will conclude. So basically, in the data center, there will be two kinds of interconnects. The first one is basically the transceivers which is the pluggable optical modules. So you can see here in the slides, the bandwidth is somewhere between 10 gigabit per second to 100 to 500 gigabit per second nowadays. So in this application scenarios, we need very high data rate per lambda. And since it is in large volume, we need very low cost. Ideally, it should be $1 per G. And therefore, the typical realization of the electrical circuits are in the SiGe drivers and TIs, which is analog amplifiers, which will be used in the optical module. And most of the optical devices were originally E35 materials. So in some cases, we need very high density interconnects, such as the switch in the data center. Basically, we need some 12 to 25 terabit per second bandwidth nowadays for the switch. Because the chip is the size of the chip is limited, we need very extreme high density of the modules. Specifically, we need very high density integrated circuits and devices. And we also need high power efficiency because the power consumption is very large and the heat will be high. So in these scenarios, the silicon photonics are believed as one of the most promising solution, which we will talk about in this talk. So basically, at the year of 2020, we have arrived at total bandwidth of 25.6 terabit per second. It's very high throughput for the payload, which is the switch, the CPU, GPU, or FPGA, something like that. The throughput keeps increasing. Also, you can see in the left side of the picture, the power consumption in these modules increases too. For example, the power for the off-chip IOs, which connects the signals, have increased even larger than the total power used for computing or the main purpose. So in this case, the optical transceivers are demanding very low power or high power efficiency, such as sub 10 picojoule per bit power efficiency, especially for some short or medium range links. So basically, previously we used pluggable optical modules, which adopts the separate optical devices and ICs. And in this case, the computing hardware and the networking hardware are separate. So these days, we know that the co-packaged optics are hot, and a lot of researchers have done or conducted. Basically, we want to make the links, especially the electrical links, shorter. We want the EO conversion placed next to the payload. In these cases, we need some very high density integrated circuits or small size optical modules. In this way, we consider the computing and networking hardware are somewhere merged. As you can see in the right-hand side, there are some publications recently, including the Intel's optical switches, especially in the optical module. There will be some high integration electronic ICs, including some SerDes, driver tiers, and also some optics. And also, in terms of the application of CPOs, in this year, published by Microsoft, it will be used much, it will have some wider applications, such as the AI training, high performance computing, or the futures data center. So basically, the bandwidth keeps increasing. At the same time, we care about the latency. So if we take a look at the implementation of electrical circuits, there are mainly two choices for the process, namely the silicon germanium and CMOS. We know that for analog circuits, especially the amplifiers, the SiGe process provide higher performances in terms of the speed, bandwidth gain, breakdown voltage, linearity, especially the noise for the receivers for the long-range optical links. And the parasitics, for example, parasitic capacitance is small and the cost would be high, but not necessary. The turnaround time is longer than the CMOS, which, for example, the MPW is around 6 months. But CMOS, we consider it, it might be more suitable for high density integration because it has the ability to integrate large scale digital VLSI, and it is probably its most promising for the switch and high performance computing. So in this case, our researches are mostly conducted on the CMOS based circuits. Okay, let's take a look at the challenges and solutions. This slide shows a typical realization of the CPO, which includes a payload IC at the left. It might be a switch or CPU, GPU, something. And it includes the SerDes for compensating for the electrical link, especially the lossy channel. The channel is not so long. It is typically shorter than 5 centimeters, and the loss is less than 12 dB or 10 dB. So if you take a look at the right, there is the optical engine. It might be realized in different form factors or realizations, but take this one as an example. There will be the electrical IC on top of the photonics IC, and the electrical signal is coupled from the packaged substrate, including some bumps, copper pillars, or wire bondings. So in this case, the EIC should include some of the XSR SerDes circuits to compensate for the loss. And also the SerDes is sometimes merged into the driver and TIA. If you can do the whole thing within one chip, the size will be small and the power consumption would be smaller. And at last, the laser could be external or in-packaged, depends. So this slide shows the realization of a typical 112 gigabit per second XSR transceiver is basically the electrical SerDes. So if you take a look, you can see the DSP is much simplified. For example, at the transmitter side, there's some 5-bit DAC and some mux to transmit signal. And the receiver side, there will be only 2-bit ADC plus CDR to simplify the hardware. The main goal is to decrease the power consumption. So in this case, the equalization is light. It's not heavy equalization. So we probably just need linear equalization, less than 10 dB compensation. And taking and for the simplified DSP, it's mostly a CDR at the receiver side, PAM4 CDR. At the receiver and the transmitter side, more bits means we can do more things. For example, FFE and pre-distortion for non-linearity. So the state of the art is around 1.6 picojoule per bit, which is 180 milliwatts for the whole thing, but at 7 nanometer CMOS. In our cases, and also some recent publications, if we can somehow merge the driver and the SerDes TX, for example, here, we can build a 2-bit ADC or PAM4 CDR to receive the signal, electrical PAM4 signal, and then process and signal and all the signaling inside the chip, we keep it in the digital domain, which is limiting signals until the output at the, for example, the driver side. If we can implement an optical domain DAC, and we can do a much simplified driver to drive the optical devices. And also, if we can implement multi-bit DAC, we can also do the FFE and pre-distortion, but in the optical domain. So in this case, the CMOS process is preferred because we can not only integrate analog amplifiers, but also digital VLSI. At the receiver side, it is also like a mixed signal receiver. For example, we have the analog input from the PD, and we can do all the following signaling, including amplification, equalization, and some kind of analog to digital conversion. If you can see here, we can implement just a low bandwidth TIA in CMOS, but optimize for noise performance. In this way, we got insufficient bandwidth. And in the following stages, we can introduce some digital circuits, include the DFE or FFE circuits to equalize the bandwidth, but with no additional noise. And in this case, this realization can be in CMOS and is preferred in CMOS because also we can integrate analog amplifiers as well as the digital VLSI. So I just show some cases real quick. First, the co-design transmitter. We know the traditional traveling wave mass-gender modulator is driven by some linear drivers. As you can see here, just a simple CML drivers can provide the functionality. But the problem is, typically the traveling wave modulator needs a very long electrode or long phase shifter. And on the electrode, the RF signal attenuation is significant. For example, maybe 3 to 6 dB attenuation. And there's we need higher swing at the input, typically 3 to 4 volts peak to peak. And also at the other end, or at the far end of the modulator, we need to implement some terminations, typically some passive terminations, for example, 50 ohm or 60 ohm resistor. This will introduce significant high power consumption. For example, we just deliver 4 volts on 40 ohm resistance. We need 100 milliamp current. And consider the efficiencies is never be 100% of the driver. So the power consumption is considerably high. For example, the state of the art of the driver typically consume 350 milliwatt, which is 3.1 picojoule per bit, just the driver, and excluding the modulator power consumption, because the VDD is powered by the modulator. And also, it's very hard to implement some large swing and linear amplifiers, which need even higher bandwidth than the limiting version. In some cases, we can implement some optical DAC. The simple one is the binary weighted DAC. For example, you can see here, we can just implement 2 segments of modulators paired to the 2 drivers. So each of the drivers just provides NRZ signals, which is limiting. And the 2 phase shifters are weighted by 2 to 1. And finally, we can get the optical domain modulation in the PAM4 format. But there's another thing we need to take care of. That is the speed or velocity match between the electrical signal and the light traveled in the waveguide. So we need to make sure the electrical signals arrive at each of the segment at the same time with the light arrived at this segment. So there will be some propagation delay control, and if we fail to do that, the output signal integrity is terrible. This is one of our work in the 40 nanometer CMOS, which is integrated with a dual segment DAC, so to build a transmitter. You can see here the driver is at left and the optical modulator is at the right side. So we got some NRZ modulation. If we just turn on one segment up to 9 dB eccentric ratio, and some PAM4 optical signals at 50 dB per second PAM4. To further improve the modulation efficiency, we consider to use some lumped segmented optical DAC. You can see here at the left side is the dual DAC, dual segment, which is still traveling wave modulators. But if we can implement some more DAC segments, each of the segment is a lumped capacitive loading, very short. For example, shorter than say 400 micron something, and we cascade it, and we implement the input signals in a thermometer coded format. Therefore, we built an optical DAC to implement the analog modulation. The synchronization problem is still there. So previously in the traveling wave, we do the velocity match by rely on the microwave speed on the T line or the electron. But in the segmented MZM, we rely on the timing skew control of the driver itself. For example, we can implement some of the delay cells and we control the delay. If we match the speed, then we can get some improved eyes. In this way, we just, in our case, we propose a phase interpolation-based timing gate technology. We just use multi-phase clocks. Take an example here. We have, for example, 90 degree and 0 degree phase clocks, and it is they are actually vectors, and we sum them and to get any phase in between. And the phase delay is just realized. So we cascade it and realize it and use the clock to gate the signal to make sure the electrical signal arrives at each of the segment at the same time as the optical signal. In this way, we match the speed. So in this case, we still need some circuit to recover the data, to make it into the thermometer code, and also to recover the clock. This is the PAM4 clock and data recovery. So we just implement the whole system in one chip. I mean the electrical circuit, and so in this case we also include some mini SerDes to act as the XSR SerDes. For example, we have an analog front end to provide some tunable equalization to compensate for the input loss. And also some gain stages to provide up to 10 dB, 8 dB gain to guarantee enough output swing for the CDR. And in the CDR, we just propose some baud rate sampling CDR, which eliminates half of the sampling phases to save power and hardware. So you can see here, we can recover the clock and recover the data and with a very low bit error rate, basically error-free, 10 minus 12. So in this way, we got the thermometer coded data and multi-phases clock. And we use it to drive the multi-segment modulator, which is a silicon photonic multi-channel modulator, as shown here in this picture. So we got some improved PAM4I still at 50 gigabit per second PAM4, limited by the electrical circuit process, which is 40 nanometer CMOS. So basically, we are trying to improve the speed now at 112 gigabit per second, but using a more advanced node. The other way to save power is the micro ring resonator. So in this case, the benefit is the modulator have very compact size, say some micrometer diameter. So it provides very small capacitive loading, and it is preferred by CMOS circuits. But you will still need to provide 3 to 4 volts peak-to-peak voltage swing. If you can drive it differentially by drive both the anode and cathode node, you can realize it in a much simpler way. So in this case, we can get some high efficiency, say high exchange ratio, and most importantly, we can achieve on-chip WDM. But the problem is the wavelength of the macro ring is very sensitive to PVT variations. In this case, the electrical and optical closed loop tuning is necessary. And in this way, the co-design is promising. So basically, this is our initial result, and for 25 gigabit per second multi-channel silicon photonics transmitter, including a 40 nanometer CMOS driver and some of the micro ring resonators. And we are still working on it. And the data rate is still improving, say 125 gigabit per second PAM4. In this case, what we need to do is not only to drive the small capacitance, but also build a feedback loop, for example, integrated on the chip, and some digital VLSI to tune or to heat up the heater, the macro ring, to tune the wavelengths in a successive approaching manner. So we also integrate some voltage DAC in the driver chip. This work is still ongoing. Next, I will just go quickly on the co-designed receiver. Basically, the TIA is the very first stage of the receiver. So it is very sensitive to the parasitic capacitance of the photodiode. We know that for the waveguide type silicon photonic PD, it shows much smaller capacitance than traditional one, especially the surface reception PD. In this case, if we want to do some frequency peaking, including the active or passive peaking in the circuit, we need to carefully match the frequency response between the PD and the amplifier. Also, we will care about the control, the bias, and the automatic tuning of the bias. Also, if we use it in a WDM macro ring transceiver, the receiver side also need to tune the wavelengths. I just show some some high-speed link techniques. For example, we build some cascaded equalizer to provide a specific equalization. For example, here up to 5 dB and 3 dB, but in multiple stages at different frequency points. And by doing that, we can somehow get very flat in-band frequency response. So this is a very early work, which is also implemented in 40 nanometer CMOS. In this work, we just realized 25 gigabit per second NRZ and up to 50 gigabit per second PAM4 optical to electrical conversion eyes. And this work is still ongoing. And actually, in this year, we have made it in 28 nanometer CMOS and 100 gigabit per second PAM4. So another way to make it compact or high integrated is to somehow integrate a PD, silicon photonic PD, to the electrical circuit within the same chip, which is called the monolithic integration of PD and TI. This is one example of the work we just implementing the CD BiCMOS process, including the 4 channels of silicon photonic PD, including couplers, TIs, and at the experimental results, we show some 40 gigabit per second PAM4 O2E either. So it is much easier to use because we just need to take care of the fiber array coupling and also the output equalization. Okay, so let's go to the conclusion. So the emerging CPO asks for high speed and low power, especially highly integrated photonic ICs and electrical ICs. We think in CMOS process, we can somehow integrate both the analog and digital circuits, and also as well as the co-packaged optic devices to make it very high integrated integration level. The most important thing is that we believe the silicon photonic PDs and modulators, which is CMOS friendly, are much preferred. For example, for the modulator, if we got some smaller voltage swing, and for the PD, we got some smaller capacitance. Also, in terms of topology, if we just implement voltage mode drivers for capacitive loading modulators, that will be much more preferred for CMOS inverter-based drivers. So in this talk, we show some co-design CMOS driver with integrated digital VLSI, specifically the CDR and DMUX, and also some co-design CMOS TI in both also in CMOS to enable higher integration. So at last, I will briefly introduce our research group, and our research group focus on the high-speed ICs dedicated for the silicon photonic and optical communication. So we start from 25 gigabit per second NRZ and to 50 gigabit per second PAM4. And to this year, we just realized 112 gigabit per second PAM4. And for the next year, we will make it more stable, improve the performance, and maybe in the next year, we'll go for the 224 gigabit per second electrical circuits. So welcome all of you, my colleagues, to find some possibility for collaboration. And thank you very much.
Thank you. I think I speak for the audience if I would say that this was a very thrilling talk with quite spectacular results and techniques that you're using there. We don't have time for a lot of questions, but let's pick one from the Q&A here by Ronald Dye. And the question is, for co-packaged optics, the industry has 2 options. The first one is near-package optics, in which the optical engine and switch ASIC are integrated on the high-density interconnect PCB. And the other is the solution by using the substrate of the switch and its organic material. Can you please review on both options?
Okay, so in my view, I think the most practical one is the organic material, maybe currently, because sorry, the most practical one is the previous one, because it's something like the onboard optics OBO, and I know in some of the Chinese optical module companies, they are focusing on this kind of co-package optics. It's not strictly some co-package, but maybe it's the most recent realization. And I think the organic one, I see many demonstrations overseas, and it really depends on the capability for packaging and substrate.
Thank you.
Okay. Mm-hmm.
There's another question in the Q&A, and people might still pose new questions, but given the time, I would suggest we continue. It might be a good idea if you check the Q&A and maybe answer the questions directly in there.
Okay, so basically, they care about the power consumption compared between the electrical and optical domain PAM4. So basically, I believe currently, if you are using, for example, not advanced node CMOS, the power consumption is even higher because you need to deliver signals into chip around 1 to 2 micrometer distance. But the point is, if you can use some advanced technology, I mean, for 50 gigabit per second, the 28 nanometer CMOS, maybe the power consumption will be greatly reduced because you can use very fast inverters and deliver the signal with low swing. Clock with a low swing, and then you can use some just limiting or digital circuits to drive the modulator to get rid of the power hungry analog linear amplifiers. That's my view. Thank you.
All right. Okay, I think with that we need to continue. So thank you, Professor Nan Qi, again for this this great talk.